Hello, so in this video I'm going to talk a little bit about higher order derivatives and also concavity and the second derivative test. Now, whenever we talk about higher order derivatives, what we kind of mean by that is that we take more than the first derivative and so on. So like if we have that you're given a function, let's say f of x equals to 4x cubed plus 3x squared plus 2x plus 1. Now I know that if I take the derivative of this, I get f prime of x equals to 12x squared plus 6x plus 2. But if I take the derivative again, I have that that's just going to be 24x plus 6. But if I take the derivative again, I have that the third derivative is equal to 24. And finally, if I take the fourth derivative of this equation, I have that that's just going to be 0. Now, all that this tells us is that basically we can differentiate this polynomial 4 times until it cancels out. Now, note that, if we were to consider a different equation, such as like g of x is equal to e to the x, well, the first derivative is e to the x. We also have that the second derivative is e to the x. Well, basically, I'll just keep repeating that and just determine that the nth derivative of g of x is equal to simply just e to the x. Now, another way of which that, that I can demonstrate on how we can apply higher order derivatives is for, like, if I have that I want to just verify that y equals e to the 2x is a solution to the equation. Okay, so we have y double minus, let's say 5y prime, and then plus 6y, and that equals to 0. Well, this is actually not too bad because essentially all that we need to do is just look at the first derivative, second derivative, and so on. So we know that y equals to e to the 2x, but the first derivative is 2e to the 2x, but then the second derivative is just 4e to the 2x. So what do I need to do with this? I need to plug it into the equation up here. So we have 4e to the 2x minus 5 times 2e to the 2x plus 6 times e to the 2x, which does this equal to 0? Well, I have that this is going to be 4 plus 6, which is 10. So I have 10e to the 2x minus 10e to the 2x, which this is actually equal to 0. So it checks out that e to the 2x is a solution to this equation above. You can also try, for example, e to the 3x. Okay, so go ahead and try that and see, if you can satisfy that equation by plugging this into here. Okay, so another thing that you may notice with higher order derivatives is that aside to the e function, how it doesn't terminate, notice that if you were to take a derivative of, let's say, for example, 1 over x, well, that equals to negative 1 over x squared. But then if you take the derivative again of this one, this gives you positive 2 over x cubed. But then if I take the derivative again, I end up with that the derivative of, say, 2 over x cubed, that's just going to be, let's see, that's going to be negative 6 over x to the fourth power. Now, if I take it again, then I'll see that basically this gives me the derivative with respect to x of negative 6 divided by x to the fourth. That's equal to positive 24 over x to the fifth power. Now, eventually, you'll be able to kind of recognize a pattern such that you would be able to say that the nth derivative, so like you'd have like the nth derivative of x, no, that should be a y. Okay, so essentially I have that this is going to be such that you have negative 1 is going to be raised to the first, yeah, it's going to be raised to the first power, or the nth power, which makes it negative 1 on the first one, and then followed by n factorial. So we have that that's going to be just n factorial, and then followed by the x variable, but raised to the n plus 1. So whenever we say like, n is equal to 1, then in that case, this gives us minus, and that gives us 1 divided by x squared. But then when it's 2, it's going to be 2 factorial, which is 2, and then negative 1 to the 2 is just going to be positive 1, and so on. So this should work out in terms of like finding the higher order derivative of the x, 1 over x to the, I'm sorry, 1 over x. Okay, so, and mostly you just try to look for patterns when it comes to higher order derivatives. Now, the thing of which that we mostly will look at though is the second derivative and concavity. So whenever we talk about the second derivative and concavity, we're basically looking at, so let's say that you have a graph, and let's say that this graph looks something like this. So if we were to use this graph, and it's just a sketch, if we were to look kind of like at the shape of the graph, like for example, right over here, I have that it kind of has like an upward direction, whereas like over here, I have that it's kind of down. Now, the way of which that we recognize that in terms of the shape of the graph is that we use the term concave. So concave up and concave down. So that's really more or less just giving us the shape of the graph. So you can kind of see that based on this little sketch, that somewhere right about here is where the concavity changes. So what we call that in this case is an inflection point. Okay, so if that's the case where you have that, you have an inflection point where concavity changes, you have to make note that it is possible for concavity to not change, for example. So like you have that with the parabola, you have that a parabola looks something like this. So I would probably say that this one is concave up, and I'm going to use just this little U symbol. It's kind of like a concave, or it is concave up from negative infinity to infinity, but here there is no inflection point. But then if I draw another graph, for instance, I could draw another graph that looks something like this. And then maybe like this. So this one you have that the concavity stayed the same. You have, or no, not the same, but it changed. So here there is no inflection point. But we have that it's concave down from 0 to infinity. And then we have that it's concave up. Yeah, let's just write it over here. So we have that it's concave up from negative infinity to 0. But again, there is no inflection point. But what if we looked at, for example, just another where you could possibly have that? What if your graph looked something like, let's say that the graph it looks like this. Then if we look at it like that, then we can see that, for example, that this function has no inflection point also. But you do have that there was a change, or no change, sorry. You have that it's concave down from negative infinity to 0, and then you have that it's from 0 to infinity. So even if it doesn't have an inflection point, you can still kind of see like what happens because it's undefined at both of these values at 0, at 0. Okay, so we can have that functions could possibly be one thing or the other and possibly not have an inflection point. But the way that we find these is by using the second derivative. So let's look at, for example, where we want to find using the second derivative test. So let's say that we want to find the intervals of concavity. Okay, but we're going to use y equals x minus 1 over x. Now, first off, I know that this is undefined at 0, so in that case, we automatically know, okay, this is undefined at 0. So we'll just add that in right here. Now, I know that I need to find the first derivative, which the first derivative is 1 plus 1 over x squared. Now, note that we don't need anything from the first derivative test, so we're just going to go ahead and say, okay, well, y double is equal to negative 2 over x cubed. Okay, so over x cubed. So here I have that this is undefined again at 0. So what that means is that I'm just going to go ahead and look at this as an interval line test, and I have that 0 is actually undefined, so there's like a hole. Now if we plug in values such as like negative 1 and 1, then in that case we just plug it back into the equation. But notice that if you plug in 1, it's going to be negative. If you plug in negative 1, well, actually that's going to give you negative as well. So what that means is that what this means is that actually, hold on. If you plug in negative 1, you end up with y double is negative 2 over negative 1 cubed, which is equal to positive 2. Oh, okay, so it should be positive. Okay, so this tells us that we don't have an inflection point, but we do have that this equation is going to be concave up. So we have that it's concave up from negative infinity to 0, and then it's concave down from 0 to infinity. And if you want, you can probably just graph this in the x and y plane and see, like, what does that look like in terms of like the concavity, because we know, for example, that this graph, it has a oblique asymptote. So we know that there's an oblique asymptote based on how it's written. And it's undefined at 0, by the way. Okay, but in this case, we have that it's concave down. Yeah, so it's concave down from 0 to infinity, and then you have that it's concave up from negative infinity to 0. Now, one thing that you can possibly look at is that there are like some x-intercepts. So you have that there's one right there, and then you have another one that's like right here. So what that means basically is that the graph, it looks something like this, where it kind of like does something like that. And then the graph does something like this. This is not really a great sketch, but it's kind of like at least giving us the idea that you have that it's up from negative infinity to 0, and then it's down from 0 to infinity. Now, if I go to the graph, which I have it right here, that's kind of what I wrote down, but the slope is kind of like not really obvious. So we have that it kind of looks like that. So kind of close, but not really. Just kind of make it at a 45-degree angle and maybe adjust it just a little bit. So let's go ahead and look at another example, which this time it'll be like a polynomial. So we'll just use that. We want to find the inflection point. For y equals x cubed plus 2x minus 3. Now this is actually pretty simple, because if we find the first derivative, you get 3x squared plus 2. But if you find the second one, you get that that's going to be 6x. Now, to find the inflection point, that's basically where the second derivative is equal to 0, or undefined or not necessarily or undefined, because like we said, like it could it could exist or not exist. So this tells us that when we set it to 0, that x equals to 0. So the inflection point, or the point of inflection, is going to be at 0, comma, uh, -3. Okay, so if you wanted to visualize that, you could, and you could also figure out, for example, like where the uh, let's see, you could probably figure out like what the sketch of the graph looks like. But notice that here in this equation, there is no critical values technically, because you have that this is always positive. So in that case, like that means that there's no relative extremas. That means that you have that this point of concav or this inflection point, um, it's that's all it is, and it just shows that most likely the graph it's always increasing, um, which is not rare, but it happens. And then you could talk about like where the concavity is, like less than 0, greater than 0, and so on. Okay, so that one was actually not too bad because it just required just finding the point if it exists or not. Now, one thing that we can kind of say is that so far what we know is that basically if you have that the second derivative is less than 0, that implies concave down. If we have that the second derivative is greater than 0, that implies that it's concave up. Now, one thing that we can use as it relates to concavity is that if we were to consider, again, like say for example, a polynomial that's unrestricted, of course, so we have something like this. Now, note that I can look at this graph and then determine where I have a max and where I have that there's a min. Now, the one thing though that we can observe based on this is that notice that the curvature of the graph is down and up respectively. So we have that right here. This second derivative is actually it's positive because it's concave up. So that means that we have a min for the second derivative when it's positive. But we have a max over here, but look at the curvature. We have that is going to be less than 0. Now, of course, if we have that the second derivative is equal to 0, that means that basically it's inconclusive, and also it's possibly an inflection point, meaning that it's probably not much. But you have to check it though using the first derivative test. So what I just wrote down is basically what we call the second derivative test. So the second derivative test says that if you have a critical point and it's less than 0, this implies that you have a max. If you have a critical point and you have that this is greater than 0, this is a min. Okay, so unfortunately though, if you have that it's equal to 0, it's inconclusive. Okay, now what we mean by inconclusive just means that it can either be an inflection point or it's really just nothing at all. But usually it turns out that it's an inflection point. Okay, so let's apply what is called the second derivative test. So the second derivative test basically says that what we need to do is look at use the second derivative test for y equals to 3x to the fifth power minus 5x to the third power plus 3. Okay, so this is not too bad because we just have to take the derivative using power rule. So we have that that's 15x to the fourth minus 15x squared. Now, in this case, we can actually factor out 15x squared. So we have 15x squared multiplied by x squared minus 1. Now this is kind of interesting because this is telling me that I have 15x squared multiplied by x minus 1 and x plus 1. So this tells me that my critical points are 0, 1, and negative 1. And you can set those equal to 0 and find them. Okay, but I'm not going to do anything with these. I'm just going to go ahead and move on to the next derivative. So when I move on to the next derivative, my goal is to basically just go ahead and take the second derivative, and I have 60x cubed minus 30x. Now, notice that basically I can take out 30x, and I get 2x squared minus 1. Okay, now be careful with this because we're not looking for technically we're not looking for the inflection points. We're looking for what the derivative is when we plug it in. So if we plug in 0 into the second derivative, well, we get that y double of 0 is equal to 0. So we're not sure. Okay, so we have that it's inconclusive for the 0. Okay, but y double, if we plug in 1, let's see, that's just going to be 30. Okay, so this one is positive, so definitely I know that that's going to be a min. But then I have that y double of negative 1, that's going to be, let's see, well, it's actually going to be negative 30, it should be. Yeah, so we got negative 30. So that tells me that this is less than 0, but that means that that's going to be a maximum. Now, basically we figured out that 0 is probably nothing because we have that it technically is an inflection point. So, or it is an inflection point. So that means that 0 is actually nothing. So 0 comma 3, that's really not going to be anything. But let's go ahead and plug this into the calculator just to verify our work. So, okay, so let's say that we go ahead and we plug in y equals to 3x to the fifth power, and that's going to be plus 5, not plus, but minus 5x cubed. And then that's going to be plus 3. Okay, so we have this nice looking equation of which it tells us that here, over here, we have that at negative 1, 5, there's a relative max, and at 1 comma 1, that there is a relative min. Now at 0, 3, that's nothing at all because you can see that it's concave down up to, in this case, it says that it's up to 0. 0, but there's also another one, by the way. Like if we look at back at our equation, there's also another one at 1, negative 1 over root 2, which is like negative 0.7. So like right about here, that's where it becomes concave up, and then it changes again, and then it changes again down over here. But you really don't need that technically, because the whole point is that we found out that 0, 0, comma 3 just happened to be an inflection point. And then 1, comma 1 was the relative max. And then negative 1, comma 5, that was the relative, actually this was the relative min, wasn't it? Yeah. Yeah. So we have that this is going to be the relative min, and then we have that this is going to be the relative max. Okay, so that tells us that that these are relative max and relative min respectively. So okay, so that's kind of like how we use the second derivative test. Now we can use it again, for example, with the following equation. So let's say that we want to try to uh, use the second derivative test on y equals 2 times x squared minus 4x plus 3 squared. Now, in this case, like this equation is very is very like it's not really tough, but yeah, like it has that you have to use like chain rule and possibly a little bit of algebra. So when we apply the first derivative test, we're going to find that y prime equals to 4 times x squared minus 4x plus 3, but then multiplied by 2x minus 4. Now notice that if you move things around, you have that this becomes 8 times x minus 1 times x minus 3 multiplied by x minus 2. Okay, so what this means is that we have that our critical points are basically our critical points are x equals to 1, 2, and 3. Okay, so we found our critical points just by setting it equal to 0. And I did a little bit of factoring there, so in case you're wondering, like, how did I do that? I just factored. Okay, so the next step is that we just need to take the derivative of this equation. So it's really just preference if you want to use chain rule or whatever. Not chain rule, product rule. Or if you want to multiply this through. You can if you want, but let's see. What I'm going to do instead is I'm going to say that y prime is equal to 8 multiplied by x squared minus 4x plus 3 multiplied by x minus 2. That way this will be a little easier. So we have y double equals to 8 multiplied by 2x minus 4. Yeah, 2x minus 4 multiplied by x minus 2. And then we have plus 8 multiplied by x squared minus 4x plus 3. Now, it looks that because we're not really technically looking for the critical or the inflection points, this means that we can actually just plug in what we need to. So this is 8 multiplied by x minus 2 to the second power plus this is going to be x minus 1 times x minus 3, and then we can just close this. Now, if I plug in 1, now notice that if you plug in 1 into this equation, well, you're going to get basically that it's going to be positive. So when I plug in y double of 1, I get that that's going to be 8 multiplied by negative 1 squared plus 0. So this is just going to be 8, which is positive. Furthermore, we can try the 2. So 2 gives me that I end up with 8 multiplied by 0 plus, okay, so 2 minus 1, so 2 minus 1 multiplied by 2 minus 3. Well, I can already tell that this is going to be negative because of the 2 minus 3. So that's going to be negative. Now the 3, let's see. The 3 is going to cancel out, and that's also going to be positive. So that's going to give you that you have y double of 3 is equal to 8 multiplied by 1 squared, and then plus 0. But I can tell that that's also going to be positive. So furthermore, I've basically figured out from just plugging it into the second derivative that it's going to be a min, it's going to be a max, and it's going to be a min. Now luckily none of these were inconclusive. So what that tells us is that we have that there's a min at 1, at 2, and at 3. Now we can basically just plug this into our equation. That way we can figure out what these are. So like, for example, if we plug in 1, now remember that your equation was y equals to 2 times x squared minus 4x plus 3 squared, but that's really the same thing as 2 times x minus 1 squared times x minus 3 squared. So basically 1 comma 0, that's your min. But then when I plug in 2, well, 2 minus 1, that's all going to be just 1, but times 2 is 2. So 2, we said, is the max. And then notice that if you plug in 3, you conveniently get 0 also. So we have 2 minimums. Now, strangely enough, if we were to graph this into the x and y plane, and mind you, you'd probably have to use a little bit more information to find the inflection points. Like you can just carry on from the second derivative if you want. Well, you're going to find that the equation looks something, let's delete a little bit of this. Okay, so I'm going to have to fix that. Okay, so it looks, a little something like this, where you have like that's going to be 1, this is going to be 2, and this is going to be 3. So in this case, like we have that this is our max, this is our min, but notice that at 1 and 3, it's the smallest min. So what that means is that this is actually not only the relative min, but it's the absolute min, and that's the absolute min as well. In the next chapter, basically, we're going to look at some curve sketching that you can use basically like the first derivative, second derivative to get the sketch of the graph based on just the just those two. So like I knew that the x-intercepts were 1 and 3. In this case, I also knew that it was to the 4th degree, meaning that I knew that it was rising to the right and left, respectively. Yeah, right over here. So I already knew that the behavior of this graph was that it was kind of like this. And that's based on just knowing where does it go as x tends to infinity and negative infinity. So basically, it's kind of like putting it all together in order to get the sketch of the graph. And we can verify this sketch of the graph by looking at, let's say we said y equals 2 multiplied by x minus 1 and squared, and then x minus 3, and that's squared also. Okay, we might have to get rid of some parentheses. There we go. So see how you have a minimum right here, you have a maximum, and you have another minimum. The y-intercept, I mean, that's a little trivial. I mean, it's just the y-intercept is 0, 18. But at least like that's one thing that you'll need when you're sketching the graph. But notice that the inflection points, they're going to be somewhere between 1 and 2, and then between 2 and 3. Um, so that's going to be a little bit of a challenge to find what were those two values right there. But it doesn't, it looks like it is 1.5 for all we know. But, you know, it could be something else. So if you want to, try to find what were the inflection points for this equation. And you can find it simply by, you know, combining all of this inside the parentheses and then just using probably quadratic formula and see like what you get. Okay, so just be sure that you go through first derivative test and second derivative test, and then from there you'll be able to find the sketches of the graph. Now, just one last thing. If you already know, for instance, the concavity, for example, then really you would know like what the function does. Like if you know that there's an inflection point at 0 where it's up and down, then in that case you can go back and figure out like what were your maxes and mins, and then what were the increasing, decreasing levels. Because basically second derivative test in a way gives you everything except for when the inflection point is the same as the critical point. That's the only thing.